Fault current calculation spreadsheets are valuable tools for electrical engineers and technicians. However, it's crucial that these tools adhere to the most recent electrical codes and standards to ensure accurate and safe results. The reason a fault current calculating spreadsheet may no longer be available on our website is primarily due to it becoming outdated. Electrical codes are updated regularly to reflect new safety standards, technological advancements, and industry best practices. When a spreadsheet is based on older codes, it can lead to incorrect calculations and potentially dangerous situations if used in modern electrical system design or analysis. Here's a more detailed explanation of why such spreadsheets become obsolete. Firstly, changes in electrical codes happen frequently. Organizations like the National Electrical Code, or NEC, publish updated versions every 3 years. These updates can include revisions to conductor ampacities, equipment ratings, grounding requirements, and short-circuit current calculation methods. Secondly, component upgrades are important to consider. Electrical components such as transformers, cables, circuit breakers, and fuses are constantly evolving. Manufacturers introduce new models with improved performance characteristics, different impedance values, and varying interrupting ratings. Outdated spreadsheets may not account for these new components, leading to inaccuracies. Thirdly, there may be calculation methodology revisions. The fundamental principles of calculating fault current remain consistent, but specific methodologies and factors can change. For example, the way conductor impedance is considered, or the application of correction factors for voltage levels or cable types, might be updated in newer code versions. Fourthly, there may be new equipment and systems. Modern electrical systems incorporate new types of equipment and configurations, such as renewable energy sources, energy storage systems, and advanced power electronic devices. Outdated spreadsheets may not have the functionality to model these systems accurately. Fifthly, there is increased complexity or greater attention to detail. As electrical systems become more complex, the need for more detailed and accurate fault current calculations increases. This might involve considering factors such as arc flash hazards, voltage drop during faults, and the impact of distributed generation. Outdated spreadsheets may not offer the level of detail required for these analyses. When a fault current calculation spreadsheet is deemed outdated, it's essential to replace it with tools that are compliant with current codes and standards. There are several options available. Reputable online calculators are a good starting point. Many manufacturers of electrical equipment, such as Eaton, Schneider Electric, and Siemens, offer free online calculators that are regularly updated to reflect the latest codes and standards. These calculators typically provide a simplified interface for performing basic fault current calculations. Commercial software packages are designed for detailed power system analysis. These packages offer advanced modeling capabilities, allowing users to simulate complex electrical systems and perform comprehensive fault current studies. Examples of popular software packages include ETAP, SKM Power Tools, and Easy Power. Engineering consultants are another option. For critical applications or complex electrical systems, it may be necessary to engage a qualified electrical engineering consultant. These professionals have the expertise and experience to perform accurate fault current calculations and provide recommendations for system protection. When using any fault current calculation tool, it's crucial to verify the results and ensure that they are consistent with industry best practices and applicable codes. It's also important to understand the limitations of the tool and to consider all relevant factors that may affect the fault current level. Here's a more in-depth look at fault current calculations. Fault current, also known as short-circuit current, is the excessive electric current that flows through an electrical circuit during a fault condition. A fault condition occurs when there is an unintended short circuit between two or more conductors with different voltages. This can happen due to insulation failure, equipment malfunction, or accidental contact. Fault current can be significantly higher than normal operating current, potentially causing severe damage to equipment, fire hazards, and electric shock. Calculating fault current is essential for designing and protecting electrical systems. The calculated fault current values are used to determine the appropriate ratings for overcurrent protective devices such as circuit breakers and fuses. These devices are designed to interrupt the flow of fault current quickly and safely, preventing damage to the electrical system and minimizing the risk of injury. There are several methods for calculating fault current, ranging from simple hand calculations to complex computer simulations. The choice of method depends on the complexity of the electrical system and the desired level of accuracy. Firstly, there is the point-to-point method, which is a simplified method for calculating fault current at various points in an electrical system. It involves calculating the impedance of each component in the circuit and then using Ohm's law to determine the fault current. Secondly, there is the per-unit method, which is a more advanced method that uses per-unit values to represent the impedance of each component. This method simplifies the calculations and is particularly useful for complex electrical systems with multiple voltage levels. Thirdly, there is software simulation. For large and complex electrical systems, computer simulation software is often used to perform fault current calculations. These software packages use sophisticated algorithms to model the electrical system and calculate the fault current at various points. The steps involved in calculating fault current are as follows. Firstly, you must gather system data. This includes obtaining information about the electrical system, such as voltage levels, transformer ratings, cable lengths, and impedance values of components. Secondly, you must determine the fault location. Identify the point in the electrical system where the fault is assumed to occur. This is typically the point where the fault current is highest, such as at the secondary terminals of a transformer. Thirdly, calculate the impedance to the fault. Determine the total impedance from the source of power to the fault location. This includes the impedance of transformers, cables, circuit breakers, and other components. Fourthly, calculate the fault current. Use Ohm's law to calculate the fault current. The formula is fault current equals voltage divided by impedance. The voltage is the voltage at the fault location, and the impedance is the total impedance to the fault. Fifthly, compare the calculated fault current to the interrupting rating of overcurrent protection devices. Ensure that the calculated fault current does not exceed the interrupting rating of the circuit breakers or fuses protecting the circuit. If the fault current exceeds the interrupting rating, the overcurrent protection devices may not be able to interrupt the fault current safely, leading to equipment damage or personal injury. Now let us discuss some factors that affect fault current. Several factors can affect the magnitude of fault current in an electrical system. These factors include the source impedance, transformer impedance, cable impedance, motor contribution, and X/R ratio. Source impedance is the impedance of the power source supplying the electrical system. A lower source impedance results in a higher fault current. Transformer impedance is the impedance of transformers in the electrical system. A lower transformer impedance results in a higher fault current. Cable impedance is the impedance of cables and conductors in the electrical system. The impedance of cables depends on their length, size, and material. Longer and smaller cables have higher impedance, resulting in lower fault current. Motor contribution is the contribution of motors to the fault current. During a fault, motors act as generators and contribute current to the fault. The amount of motor contribution depends on the size and number of motors connected to the electrical system. The X/R ratio is the ratio of reactance to resistance in the electrical system. A higher X/R ratio results in a higher fault current and a slower decay of the fault current. Now let us discuss the importance of accurate fault current calculations. Accurate fault current calculations are essential for the safe and reliable operation of electrical systems. Underestimating fault current can lead to inadequate overcurrent protection, resulting in equipment damage, fire hazards, and electric shock. Overestimating fault current can lead to unnecessary tripping of circuit breakers, causing disruptions in power supply and reduced productivity. Accurate fault current calculations are also required for arc flash hazard analysis. Arc flash is a dangerous electrical phenomenon that occurs during a short-circuit fault. The intense heat and pressure generated by an arc flash can cause severe burns, blindness, and even death. Fault current calculations are used to determine the arc flash hazard level and to select appropriate personal protective equipment (PPE) for electrical workers. In conclusion, fault current calculation spreadsheets can be valuable tools, but it's crucial to ensure that they are compliant with current electrical codes and standards. When spreadsheets become outdated, it's essential to replace them with tools that are accurate and reliable. There are several options available, including online calculators, commercial software packages, and engineering consultants. Accurate fault current calculations are essential for the safe and reliable operation of electrical systems, protecting equipment, and preventing personal injury.